All. This is Dr. Mobeen Sayed from drbeen.com. Welcome to one more show. My favorite day today. We will have a tiny bit of an open forum. We would exchange the Zoom link or share the Zoom link, and then we will do Zoom as well today. So let's just have some audience build up so they can see the Zoom link. So how is everyone doing? And um, Ruby Zared is saying, I already hit the like button, so thank you very much. Were you able to watch the FLCCC video? Can I share a tiny bit of this with you? Let me see if I can find the link. And how is everyone? So if I go to FLCCC Press and go here. So let me just very quickly share my screen. It is going to be weird that you're going to see me screen in screen as well. So this is the channel FLCCC Press, and this is the video here. I think doctors had lots of good things to discuss. I think it was amazing, and I would love to see how you find it. Hello, Samina, how are you? Yes, so I thought that I had put the link in the description as well. I was cracking up that in this FLCC's video, Dr. Pierre Corey and I think Carolyn and France and M. St. Clair and some other cool beans were discussing the beanery beans thing. And so that was so fun to watch. So Carolyn says that I thought it went very well. I thought that too. I thought that there was interesting information and talk there. Twin beans is a very interesting name. Nancy says, sad I dropped a bottle of wine. Sorry, Nancy, I laughed. My apologies. I don't drink. So, and apologies. Jean says that video was excellent, informative, and hopeful. Absolutely. Rima says, Dr. Bean, of course, has the most hair and best skin. So yeah, so my hair would be their own departure as well, Rima. So who knows how long. So I can probably enjoy them as long as I got them. Ifia Carter says you were a wonderful moderator. Thank you, Ifia. Heart beating tonight. For me, what was important was that by my mistake or due to my personality flaw or any such thing, I don't end up causing their discussion points to be drowned out or the video not to be good. So that was I wanted to be as transparent in that discussion as possible. Nancy says, Shabbat Shalom. So what is the answer to this? Is the answer to repeat the same? Shabbat Shalom? Yes, so Sherry, there is a has been already. Siddhartha, how are you? How is New York? Coco Bean, I love that. Thanks to all that you do, my first time of chatting. Welcome, Coco Bean, and thank you very much for taking Coco Bean. Oh, I love this one too. Ruby says nutty beans. Very nice. We have lots of beans. Nina here. How are you, Nina? How is Jenna? So here is Jenna. New CDC guidelines, 3 feet instead of 6. Really? CDC is just all over the place. Jenna, hopefully you're doing good today. You went for IVIG. M. St. Clair says, Dr. Bean, you don't have any big personality flaws. You are a good man. Thank you very much. So Sometimes I bait you to kind of tell me these good things that make me feel better. This is one of the pandemic treatment for me. uh, 3 feet, it's really 26. Ditching the grind. Hello, everyone. Hello. Uh, so how about we do this? We are about 188 here. I just wanted some more folks to be here, and I share the link and we go to Zoom. Do you want to, in the meanwhile, just 10-15 minutes, talk a little bit more with drawings about diabetes? We can continue that discussion tomorrow as well. But if this is something that you are interested in, I can start that. Or if you just want to have fun today, it's a Friday, then I can share the link and we go to Zoom. Lisa's name, More Bean. That is awesome. So what did Jenna say something? People are saying, sorry, Jenna. So let's see. Where is Jenna? So my infusion was canceled because I woke to flight. Oh, sorry about that. So it's better than I was thinking what happened to Jenna that everybody's saying sorry. Jealous Jackie. That is nice. Okay. Got it. I understand. So let's talk a tiny bit about diabetes. We'll start putting the foundations together. I think that diabetes, hypertension, cancers, respiratory illnesses, renal illnesses, and liver problems, GIT problems, these are some bigger things that we all at some point in our life are either going to have them or already suffer them, or our loved ones. So it is interesting to have some background to these things. So Hussaini says diabetes and Modi. So Modi I may not be able to do today because there's a lot. So let me just start some basic concepts of diabetes. And then we'll build upon them. We'll go deeper and we will build upon them. But I'm going to bring us to a very initial phases of diabetes. So let's do it. Deborah is here as well. Deborah, you've been here after a long days, huh? Debbie Boss, Jen, I have CVID and IVG if you need any help or support. Thank you, Debbie, for doing that. Okay. Lissy says, your classes are superb. Thank you. Okay, so let's very quickly look at some of the concepts with diabetes. And we'll go from there. So you can see my screen, I hope. So I'm going to talk about the mainstream diabetes-related concepts. No conspiracy theories, so mainstream, textbook medicine. So let's start with it. First concept. So we'll go one concept at a time. So the first concept is that eventually our cells need one glucose molecule to be brought into them, and that glucose molecule goes through multiple metabolic steps to finally release energy. And the energy that it releases is captured in the form of ATP. So whenever I think about ATP, I always think about ATP as the little tiny batteries in our cells. And these are, imagine if the cell was a universe or a country or an earth, then within it needs to have lots of energy resources to be able to use them where needed. So these ATP are usually the energy resources. And in here, the TP, the triphosphate. So let's say this is adenosine. Just imagine adenosine to be any building block, something to hold phosphates. Imagine if you have a glass of water. So the glass itself is adenosine. And in there, we have put water, which is the actual thing you're going to use. So just imagine this is adenosine, and it is some molecule that can hold phosphates. Guanine can do that as well. So there are other molecules too that can do it. So this is one phosphate. Phosphate is the currency in our body. That is the energy in our body. So every phosphate bond has energy in it, which can be stored. And then when you break that bond, that energy can be released and used. So normally, so let's say this is one adenosine and it has one phosphate attached to it. We'll call it adenosine monophosphate. So one phosphate. Normally, monophosphate structures do not like to give away their phosphate. You can call this a poor cell. It is a poor cell and it only has $1 and it does not want, I'm calling it a poor cell. Let's call it a poor molecule. And it only has $1 and it does not want to give that $1 away. So it really is difficult to break that one bond. But we can actually build another bond with it. So we can give this molecule $1 more. So now this would become adenosine diphosphate, $2, 2 phosphates. And then we can even give it 3 phosphates. A third one too, adenosine triphosphate. So this is the ATP. And when we have ATP, the easiest bond to break is the third one. So if somebody has $3, taking away the third dollar is the easiest. Then it becomes, that molecule becomes a little conscious and says, oh man, I lost $1. I'm going to become poor if I lose more. So it holds a little tighter to the rest of the two. And it is a little more difficult to get the second one out as well, but it can be. And then it is much more difficult to get the last one out. So that is the basic concept. So usually this molecule goes from ATP, gives energy, and becomes ADP. And then usually from ADP, it catches a phosphate and becomes ATP again. But you would see that sometimes from ATP, it will become ADP. From ADP, it will become AMP. And then from there, it would then cycle back and get one phosphate and become ADP, then get one more phosphate and become ATP. So this is the kind of cycling that continues to happen. Usually, we do not have AMP breaking down to just adenosine in normal cycles. Good? So the point of this part of the discussion is that we need to make ATPs for all the functions in the cell. Every function in the cell needs money. The money in the cell is triphosphates. So every business in the cell is transactional. You want something to move from here to here, you have to give money to get it moved. You want something to be built, you have to give money to molecules, enzymes to build something. You want something to be destroyed, you have to give money to the enzymes to destroy them, and that is the energy. And how do we pay these cells to do their function? Every day when we eat and breathe and drink, we are actually bringing in fuel for these cells. That is our payment to the cells to continue to work. And if we cannot bring in that payment, then that would not work. And if we don't have our own real life dollars, then we cannot bring in payment for these cells, and these cells would start starving with us as well. So this all is money game. Now inside, the glucose is the most important one. Of course, proteins are there as well and fats are there, but today I want to focus on glucose. What happens is this: once the glucose arrives in a cell, the way this whole thing happens is this. Imagine we have pancreas. In the pancreas, we have cells which are called beta cells or beta cell. These beta cells, so I'm going to call them beta for my purposes. These beta cells have, so if I make this here like this to kind of make a complete cell, these beta cells have doors in them. So let's say, not doors. Imagine these beta cells have a channel in them. We call them GLUT, glucose transporters, glucose transporters, or GLUTs, G-L-U-T, GLUT, glucose transporter. And there are multiple kind of glucose transporters. Normally for cells, the insulin is the one that helps open the glucose transporter so that the glucose can go in. But in the case of pancreas, the beta cells in the pancreas, the beta cells, they have glucose transporters that are always open. They do not need insulin to open. They are always open. The benefit for them to be open is that whenever we take food, eat food, and whenever we get glucose from that glucose can very simply get into this cell through these transporters, because their doors are always open for glucose. And why is that? Why do we have beta cells in the pancreas who have, or which have, I do not know what is the right salutation for these cells over here, who have the glucose channels that are always open? The reason is that they are really tiny glucometers. They are tiny glucometers. And there are billions of them in our pancreas. So what happens is every cell acts as a glucose metering system. That means it needs to understand what is the level of glucose in our blood. For that, it has this channel here which allows glucose to freely move into the cell. That way, the cell can measure how much glucose is pouring into me. And that would tell the cell how much glucose is present outside. So let's say this is the glucose level that has poured into this cell, correct? And this would tell the cell how much glucose is outside. When the glucose outside increases, then the glucose inside increases as well, because the glucose channel is freely open. So this is a tiny glucometer. What does it do with this? Once it measures the glucose level, so let's say it knows that, all right, the glucose level is now increased more than what it should be. This cell can then make insulin and release that in the blood. So what is the function of this cell? Imagine you are a beta cell in pancreas. Your job is to continue to measure the amount of glucose present in the blood. Your job is to keep that glucose level, let's say at 80 nanograms, some level, 80, 90, 100, but 80 milligram per deciliter. Let's say that's your job. So what you are equipped with, what you're given is a measuring tool. So you are continuously measuring that, hey, what is the blood glucose level? And then based on that measurement, you are given the capability of making insulin. So whenever the glucose level goes above the standard level that you want, your job is to make insulin and release in the circulation. That insulin's job, in turn, is to get the glucose that is present outside, for example, in the blood vessels and in the tissues. The insulin's job is to go and rush that glucose into other cells and say, hey, glucose, get into the cells. We are not liking it that you are too much. You're just running around. So imagine a school, children from a school, 200, 300 children visiting a place, a neighborhood, all of them running around in the streets. That is what's happening. That is glucose. And glucose is high energy, and I'll explain why it can become really bad. So for the time being, just know that when the glucose is more, the beta cell has measured it, and based on that, it has released a bunch of insulin to say, insulin, why don't you go and get the glucose in the other cells? Insulin would go in here, and now these other cells, the tissue cells, they also have glucose channels in them, or as we would call them, glucose transporters or gluts. So these also have gluts, glucose transporters. However, these gluts need insulin to come and convince them to open up. So they are not normally open. Their doors are normally closed. So what happens is when insulin arrives, insulin binds there. So let's say this is insulin. It has bound here. When it binds to the glut, glucose transporter, then that glucose would open up. The transporter's door will open up and glucose can go in. So this is like all those children running around on the street, and somebody comes in and announces, hey, neighborhood people, open your doors, let the children come in the homes. And then everybody opens the door and the children go in. So that person who is announcing is insulin. And where did that insulin come from? the beta cell. Why did it come from there? Beta cell felt that there is more than normal glucose levels that should be there. So it is saying, fine, we need to get that glucose in the cells. So when the glucose starts going in the cells, of course, the glucose amount in the tissue and in the blood would start dropping because glucose is entering the cell. As the glucose levels start dropping, this cell here, the beta cell, would now start feeling that, all right, glucose levels are going down. So as it senses that the glucose levels are going down, it would start reducing the production of more insulin. So imagine once again that you are the beta cell, and now you were measuring glucose, and it was at 140 milligram per deciliter, and you said, insulin, go get the glucose in the cells. And insulin went and did its function and moved the glucose in the cells. And because of that, in the blood and tissues, the glucose level fell down to, let's say, 90 milligram per deciliter. And now the beta cell or you said, okay, I can release less insulin now. The levels are coming to where I want them to be. And so you would keep doing it till the time that the glucose level goes back to 80 milligram per deciliter. This is why what we do is we say, when you take a meal which has carbohydrates, your carbohydrates levels, or the glucose level, will go up because of the meal. And as the level goes up, the insulin level will also then go up. And that insulin level that goes up will cause the glucose to get driven in the cells and start going down. And as that starts going down, the insulin level would start going down as well, till the time that the glucose level comes back to, let's say, 80, and then insulin levels will fall below to say, okay, I don't need to push glucose anymore. So this is the usual behavior and relationship of insulin and glucose, and the relationship of beta cells function to the insulin levels and glucose levels. Now, what beta cell do is another very interesting thing, and what our body does. Usually, if you take a meal now, let's say in many folks' homes, it is supper time, it's meal time. So let's say you take a meal now. It is 6:23 with me, and I eat my dinner now. What happens is there will be a spike of glucose extracted from that dinner material and brought into the liver and brought into the blood. And there will be a peak of glucose. Of course, that means there will be a corresponding peak of insulin. And within 2 hours, usually, in normal healthy individuals, within about 2 hours time, there is within this 2 hours, there is a continuous absorption of the glucose from the meal, and there is a continuous release of insulin after sensing the glucose level from the meal, and that insulin is released in the blood. And within 2 hours, that glucose has been received, pushed into the cells by insulin, and the glucose level in the blood go back to 80 milligram per deciliter. Done. Now the problem is, we do not have glucose anymore. The person has stopped eating. They ate something, and we used that up to push that into the cells within 2 hours. That energy is stored. This is like if you went out for groceries, you went out for food, and then that food is stashed away in fridge and storage and other places, pantries, within 2 hours. And now you want the remaining time, let's say from this meal to the morning, there are going to be 10 hours. For this 10 hours, our bodies still need glucose, because even when we are sitting at rest or we are sleeping, our cells are continuously functioning. That is called the basal level of activity. And our cells, when they are functioning, they need energy, and that energy has to be mostly in the form of glucose. They can take protein, they can take fat, and I'm not talking about that at this time. We are focusing on glucose. So where do we get that glucose from? The glucose that is present in the blood and tissues, outside of the tissue, we call it interstitial fluid, the spaces between the cells. That glucose is taken up, it's moved into the cells. Now we are at a place where the glucose levels are just barely enough to maintain a basal level. And when the cells are still functioning and they take more glucose, the glucose is now going to start falling. So what is, if there is no further glucose provided, that means you have gone to sleep, you're not eating anymore, then what would happen is glucose level would start dropping. And if that happens, eventually the glucose level would reach zero. By that time, we would have died. But this does not happen. We go to sleep, then we wake up in the morning, and things are fine. So what happens? During this time, as we call it in medicine, fasting hours or fasting time, during this time, what happens is our body mobilizes the glucose from the storage. So a main storage is liver itself. When we eat something, that energy, that the food particles, carbohydrates and other things, they go to liver first. Liver is a very responsible person, responsible person living in our body. And what it do is it actually stores glucose with it for such times when the fasting occurs. And when the fasting will occur, it would take those stores of glucose, mobilize them, and release glucose in the blood. Liver is one such tissue. Then our cells, for example, fat cells, will also store glucose. And then when time is, we are in the fasting state, they will release fatty acids and eventually glucose will be formed. Then muscles also store glucose, but muscles, the muscle look like fish, so I call them shellfish. Muscles can actually release glucose or mobilize glucose from their own stores, but they do not give it out to other tissues. They only use it for themselves. So that means when a muscle is hungry or it is in a fasting state, you are not pouring glucose in it from outside. That muscle can mobilize its own stores and use those for its own needs. Other tissues like liver or fat and other tissues, they can release glucose in the blood for others to be to sustain their lives as well, other cells too. So that is the storage. And that storage allows the glucose to continue to release so that we are actually going to continue to maintain our 18 milligram per deciliter. So we don't actually go down to zero and we don't die. We just continue to have glucose. This glucose is coming from storage. Then again, you take another meal, carbohydrates go up, insulin goes up with that. And then those carbohydrates cause the glucose to be pushed into the cells. Insulin goes down as well. So the carbohydrates are pushed into the cell by the help of the insulin. And again, those cells that now receive the glucose, for example, liver, they would start storing it. Fat, they would start storing it. Muscle, they would start replenishing their stores as well, and so on. So whenever glucose is received, it is stored and used. And that is the cycle that is always continuing. This is like whenever you get your pay, you always save some part and you use some part. And then when you don't have enough funds, then you go and dip in the saving and use that. But the next pay, when you receive it, you replenish your saving again. And this is the kind of cycle that continues in our body. Because of that, we never reach a point where the glucose is at zero or so low that we die, even other than when the time is there that we are dying. So this is how glucose cycle works. So if you like, I can go to the next concept, that when glucose is increased, what is bad, or we can continue tomorrow and now hop on a Zoom call. What would you like? Don says the dietary requirements of carbohydrates is zero. Don, let me say, we can get ATP to support your point. We can get ATP from um, proteins as well. We can get it from fats as well, and we can get it from glucose too. Ketones, absolutely. Proteins can do those things as well. So that's a different discussion. I do want to make sure that we focus on glucose, diabetes, and understand that. And then what is the right nutrition? That's a different concept. We can talk about that too. Okay, so Lisa says next concept. Ruby says Zoom. Steve says the closest thing to my heart, like Siddhartha says either. Okay, so let me do this. I'm going to attach one more concept here, and then we would hop on Zoom. Then in terms of insulin, diabetes, we'll work with that concept because this concept is kind of fresh in our mind. So now we know that when the glucose arrives, we have glucometers. Those glucometers give us insulin based on the amount of glucose received. That insulin would allow the glucose to be pushed into the cells where it will be converted into ATP and stored like energy. The glucose itself can be stored as well as glycogen, which can be then mobilized later on. So we all know that now. Now, why do we get diabetic? What is the problem with glucose? And this is a very interesting and easy concept. And interesting for me that I see medical students, and when I was a student, I did the same. I see medical students kind of cramming, remembering, recalling, and repeating why glucose causes or diabetes causes issues and what kind of issues. But if we actually understand what glucose does, then we can pick up any tissue and we can say what will happen to it. So let me give you that formula that would then free you from trying to remember the side effects of diabetes. But you can actually look at any tissue and say, okay, this is what would happen. So let's see. Let's say there is a cell here. And the cell has its surface. On the surface of the cells, we have usually proteins, the cluster of designations and receptors and cilias and many other things. There are proteins present on the cell surfaces that are functioning. You know that, for example, on immune cells, we have toll-like receptors, we have PAMs, we have various ACE2 receptors, ACE1 receptors, and all such things are proteins that are present on the cell surfaces. Imagine an endothelium cell. That is a cell that is lining the blood vessels. Its surface is usually very slippery, but it is not by chance that it has become slippery. It has become slippery because it has kind of proteins and glucose is out here that make it like a slimy layer so that the blood cells cannot come and attach to the endothelium and they can just slip away. And that is sort of a prevention of clotting, because if the cells would start stopping here, then they would start clotting here as well, which is bad. So these are slippery surfaces. Then if you look at the respiratory system, we have cilia on the cell surfaces. Those cilia's job is to propagate and beat and take the phlegm out and so on. Meaning the basic takeaway from this part of the discussion is on the surfaces of the cell, there are structures that are doing functions. This is just like on the outside of your home. You have door that opens outside and closes it. You may have windows. You may have light fixture. You may have other things that are installed outside the home that have specific functions. When glucose is present in the vicinity, when glucose is present here, in the blood or in the interstitial tissue, if I can just very quickly make it, let's say this is a blood vessel. And then around that blood vessel are cells, right? So these are cells. Between these cells are spaces. So if I put them all, these cells, on a surface, just like imagine homes, right? So these are the cells that are present. And then, of course, there is open space between them. Although it is a microscopic space, but there is space between the cells. This space is called interstitial space. Stitium means tissue. The cells are the tissue. And the space between the tissues is called interstitial space. And here we have a blood vessel. This is a blood vessel that contains blood, and blood has multiple things in it, red blood cells and white blood cells and all that, but it also has nutrition, it also have oxygen. So those things just keep coming out of this area, including glucose. So the glucose that is present in the blood vessel is equated, it is in equilibrium with the glucose that is present in the interstitial space. Then is that the same amount of glucose inside the cell? That is not true. That would depend upon the amount of insulin present, because glucose in the blood vessel will then enter the interstitial space. From there, to get into the cell, it needs insulin. And this is where diabetes comes in, that if we have less insulin, then there is glucose present in the blood vessel. You have eaten food, you have glucose. Even if you did not eat carbohydrates, your proteins that you ate, keto food, for example, those proteins are going to make amino acids. Those amino acids are going to be converted to glucose. That glucose is going to be needed inside the cells. So glucose is present in the blood vessel, and then equal amount here as well. In diabetes, because that glucose cannot enter the cell, it would just continue to increase in amount in the blood vessel and in the interstitial tissue. It would just keep accumulating here. Some of it is going inside the cells as well, but majority is just accumulating here. So now the question is, what's so bad about glucose accumulating here? That is the answer that I think if we get that today, we'll get a majority of the concept and we understand why the diabetes causes problems. So let's look at that. Imagine these guys are glucoses. They are just hanging out. And all of a sudden the person becomes diabetic, and now there are like tons of glucose. There is a lot of glucose here everywhere. Glucose outside though. Outside the cells, not inside the cells. Cells are starving. Glucose is not able to get in because there is not enough insulin, or there is enough insulin, but the doors are still not operated by the insulin. Imagine somebody putting in super glue in the door's locks. So insulin is there and saying, please open the door. I want the kids to go in the home. But the door is not opening up because it is super glued there. And we'll talk about how it can get super glued. But at this time, the point is, we have a bunch of glucose outside. This glucose outside. So now here is a very important concept, equally important for medicos and for non-medicos, because I see medicos getting struggling with this concept a lot as well, including medical students. And that is, there are two basic effects of glucose. One is called non-enzymatic, and I'll explain this in a second. Non-enzymatic glycosylation. I do not know if the spellings are correct. Glycosylation or glycation. And the second concept, or the second mechanism, is osmotic pressure. Osmotic pressure. These are the two primary mechanisms by which glucose causes damage. And now let's go from head to toe and understand how does this happen, and we would know why diabetes does what it does. So first of all, let's understand, what does this mean? Non-enzymatic glycosylation or glycation. What that means is, normally these surface structures, the proteins or the cell surfaces, if we want to attach something to them, we will need some enzyme which will charge us some money, that is phosphates, energy. And then it will take something that we wanted to connect there and it will connect it there. That is called enzymatic whatever ation. So let's say if we want a glucose to be attached here on the cell surface, we will need an enzyme that can pick up glucose on one end, that can bind glucose on one end, just like ACE2 bind coronavirus on one end and are bound to the cell on the other end, and then they just bind them. So we need some sort of an enzyme that can bind with the glucose. Then it can also bind with the cell. So this is the enzyme, binds here, and then puts them together. This is called glycation. Glycation means attaching of glucose to something. And sometimes we need it. We make glycolipids, which are lipid molecules with the glucose attached to them. Remember, we looked at hydroxychloroquine, that one function of the hydroxychloroquine was that it prevents the glycation of the last amino acid of the ACE2 enzyme. So this is the ACE2 enzyme. And when it is being built, one last brick of that has a glucose attached to it. That is called glycation. And so glycation needs enzymes, and it is a very normal, natural process. However, when the glucose is in very large quantities, then what happens is that glucose would just willy-nilly start getting attached wherever it wants. This is called non-enzymatic glycation. Enzyme was not present. The person who was regulating the attachment was not present. It just started attaching wherever it wants because the concentration is so high. This is like the children are so many in the street that if you open the door, not just your own children come in, but there are so many more children that came in as well. And there is no regulation there. So that is a non-enzymatic glycation. This non-enzymatic glycation causes the function of the surface proteins to become disrupted. For example, if it is a cilia is not going to work correctly. If it is, let's say, ACE2 enzyme, it is not going to work correctly. And please don't take glucose to disrupt the ACE2 enzyme. It's not going to happen. I'm just making up an example. Or for example, if it is a endothelial cell surface and glucose gets attached to there by non-enzymatic method, then that cell will become damaged. It is just like this, that if your window is not operating correctly and you try to force it to work, it might break. That is the same thing when glucose starts attaching to these things. These proteins, when they try to work, either they cannot work, or if they try to work, they start getting damaged. So that is one destructive effect of extra glucose present in the system. The second one is osmotic pressure. Osmotic pressure is that wherever glucose goes, glucose loves water. So does salt, right? So if this is glucose, it is a sweet little thing. And this sweet little thing, let's make it a little cute as well. It loves water, and water just stays with it all the time. There are lots of water that just hangs out with glucose. That is the osmotic pressure. It binds water with it. This is why when we eat carbohydrates more than, let's say, proteins or fats, and when the glucose is stored in our body, it stores a lot of water with it, and we become more fat and squishy. On the other hand, if we are taking less carbohydrates and more proteins or fats, then when these things are stored, they do not hold water with them. And because of that, even when we have energy storage, we are not that squishy and softy. So glucose loves to have water with it. So that means wherever glucose is going to sit, it's going to have water with it. And now let's see. So keep these two things in your mind. Now let's see the effects of diabetes. We're going to go from head to toe. So starting near the head, let's start with the eyes, lens. So here is the lens of the eye. When glucose enters in the lens, it would be converted into ATP and the energy is taken and the remaining glucose is gone. But here we do not have enough insulin to come in and get the glucose actually to be used up outside of the lens and then to be removed from the lens to be used somewhere else. So the glucose that has entered the lens is just sticking there because outside is enough concentration as well that this glucose doesn't need to come out. And when it is there, it is going to keep water with it as well. So what is that effect? That is osmotic effect. The result is that this lens of our eye will swell up like a balloon. Why? Because it has glucose sticking in it, and that glucose has its friends with it as well. They all are having a party in our lens, and they're just sticking there. And lens have swollen. The result of that is we cannot see clearly because the lens is not focusing. What is this effect? This is osmotic pressure effect. And again, medicos or medical students, they just start cramming that on the eye, the lens would swell up because of glucose. No, just see what glucose is doing here. Then let's look at the retina. Here, retina has blood vessels that are supplying it, correct? These blood vessels in our retina are very tiny, very small, cute blood vessels, and they have to be very thin, like capillaries, and even thinner, because we don't want them to be blocking our vision. This is like if your TV screen is showing all the wires and the components through it. So we don't want that to happen. So what happens is these are very tiny little delicate blood vessels. When glucose is present, I'm going to make one of these blood vessels in a bigger structure. And now let's say here is the endothelial cell, here is another endothelial cell, another endothelial cell. So these are the cells in this blood vessel. Although usually they're one cell thick. But anyways, go with me for a second, please. So these are the cells. What glucose does is it gets stuck on the surface of the cells. So you tell me, if we have a very narrow, tiny pipe-like structure, and in that there is glucose or mud sticking in it, do you think that the lumen meaning the little space in it through which fluids are moving in and blood is moving in and out, do you think that place would stay intact? It is, if you fill a pipe with mud, do you think that pipe will be able to function correctly? It will not. So here the blood vessels are now filled with glucose attached to their endothelial surfaces. It can then go underneath the cells as well and start accumulating there. That would cause hardening of the blood vessel. Then it would cause inflammation. That would cause atherosclerosis. Eventually, it can even block these blood vessels. But let's start in the beginning. The blood vessel has now become narrow. When the blood vessel is narrow, it would provide less circulation to the retina, and the retina would start dying. What is this? Is this osmotic pressure effect, or is this non-enzymatic glycation? It is non-enzymatic glycation. The glucose has just gotten stuck on the cell where it should not have. That is a retinal damage. So one reason for the retinal damage is the blood circulation affecting, which is going to retina. So two damages in the eye. The third damage. So we know the retina, the nervous system layer of the eye that is sensing, like a camera lens, or camera sensor, not lens, like a camera sensor that is sensing the light. That layer is eventually connected to the optic nerve, the nerve that would take this message from here all the way down to the brain. Optic nerve, like other nerves, may have myelin sheath on it. Myelin sheath is another set of cells that are, this is like wrapping on a wire. So if the electrical wires have plastic wrapping on them, correct? Our nerves have many of the nerves, or you can say those nerves that need to conduct faster. Those nerves have this wrapping on them. There are nerves that do not need to conduct faster. And I'll give you an example. If you accidentally touch hot stove, you would actually recoil your hand, but you would feel the heat or the burning sensation a little few moments after, because the signal from the nerve to the brain takes time to reach there. But on the other hand, if you want to move your hand, you could move them as soon as you think. And now it is not that you thought you want to move and then a few moments later the hand clasps. That is because the motor nerve is working very fast. Why is it working fast? Because it has myelin sheath on it. This myelin sheath, its job is to allow the electrical current within the electrical wire, the neuron, to jump from one gap to the next gap. And this is called jumping way of transmission. Not a very big deal at this time. But what is important is that this myelin sheath cell, this cell, is very important for the correct transmission and correct speed of transmission of the nerve signals. Glucose can enter in this cell as well. It enters everywhere. When it enters there, and let's say the person is diabetic, then the glucose is going to be entering there, not getting too much used up, but just accumulating inside the myelin sheath, just because of the mere concentration outside that it would be pushed in. And now when it is there, imagine when you open the door for the children, instead of 2 children coming in, 100 children come in. And now they're just hanging around in the home and saying, hey, how's it going? And you have 100 children in the home. The same is the problem here, that there was so much concentration of glucose outside that if you opened a glut, there is a pile of glucose that came in. And now this myelin sheath cell would swell up, because not only the children came in, the glucose, it brought lots of water with it. And now this myelin sheath cell has become swollen. So let's say this is the nerve in it. The cell has become swollen. This swollen cell, this big cell now, is in trouble. What is the trouble? If it continues to swell like this, it's going to burst open. It's like, if you have a balloon and you keep filling it with water, eventually the balloon is going to pop. This cell is going to pop. When this cell is going to pop and the myelin sheath is destroyed, that is what happens in multiple sclerosis as well, that myelin sheaths are gone. So when the myelin sheath is destroyed, the cells are destroyed, then the wire, the nerve itself, is now naked inside. The nerve is present and it is not functioning correctly because the transmission speed is destroyed. And so now a motor nerve that was supposed to, motor nerve meaning a nerve that is moving my hand, for example, it was supposed to move very fast. The electrical activity was supposed to go very fast, but the myelin sheath is destroyed because of the extra glucose in the myelin sheath and popping those cells. And that causes patches of absent cells or covering on the wire. And now wire is not conducting correctly. And maybe the wire to this finger is not conducting correctly and the others are fine. So when I'm moving, one part of my hand is not moving correctly and the other is moving and I am uncoordinated. That happens in MS as well. This can happen this is the diabetic neuropathy. So here, in this case, the transmission of the vision is also disrupted because the myelin sheath is broken. So lens is affected by osmotic pressure. The blood supply of the retina is affected by non-enzymatic glycation of the blood vessel. These blood vessels would start popping and destroying as well as the time continues. Myelin sheath is getting destroyed, and that is causing nerve signal issue. There are 3 issues in the eyes. If we go down from there, let's go to our chest area. And so we have heart and lungs over here. Let's go to thymus area here, and we have, let's say, immune system. Immune system cells have double problem. One is that they do not have enough ATP in them to be able to function correctly, so they cannot fight infections very, very well. And secondly, their receptors are all now non-enzymatic glycated. Imagine with the toll-like receptor, there is a glucose molecule hanging there and saying, hey, I'm here, and the poor receptor cannot function correctly. Imagine if there is a child that is hung with your hand all the time. You're trying to cook something or write something, and there is a child who's hanging here. Would you be able to function correctly? No. So immune cells cannot function correctly as well. That is why diabetics get in lots of infections, or their infections are not healed correctly or fast enough. And there are two reasons for that. Number one, the infected tissue. So let's say there is some tissue that is infected. This is that tissue. Number one, the blood supply to that tissue is affected because of this non-enzymatic glycation of the endothelium of the blood vessel, causing narrowing of the blood vessel, and the enough blood is not arriving there. And I had to tell you one more thing over here. This nerve here is not only not conducting correctly because the myelin sheath is popping. This nerve is also further impacted because the blood supply of the nerve itself is also affected because the blood vessel has non-enzymatic glycation in it. And the blood vessel cannot conduct or bring in enough nutrition freely. So the nerve has double problem now. One, its myelin sheath is popping. And second, it doesn't have sufficient blood supply to it to function correctly. So it is in ischemic state and dying. The same thing is happening here. This tissue is not getting enough correct nutrition to be able to fight with viruses and bacteria. On top of that, even if there is a white blood cell that would come in here to help, or a macrophage that would come in here to help through this narrow blood vessel, they would still not be able to help very much because they don't have energy. So if there is a virus here, let's say SARS-CoV-2, do you think that virus is going to be cleared out easily? No. One, there is not enough blood supply to bring in nutrition and immune cells to kick the virus out. Secondly, even when the cells come in, they can't do much. They are just all lazy cells. So that is a problem with, let's say, immune system. Then if you go down to the heart, same problem. Number one, not enough energy. And number two, the endothelium, the surfaces of the blood vessels in heart are coated with this muddy glucose. And that once again would hinder with the blood vessels. And more problem for the heart is not just direct damage to it. Heart's problem is, why it is crying is that it has to push blood out into our blood vessels. And our blood vessels are coated with glucose as non-enzymatic glycation of the endothelial surfaces has occurred. So imagine if I give you a tiny straw to blow through, but that straw is clogged with lots of things in it. And I ask you to either suck the, let's say, tea or milk or whatever, would you be able to? So I know this from boba. So I love boba tea. There is lots of boba tea around here. I live in Cupertino. Sometimes the boba gets stuck in the straw. And so whatever you do, it does not move. That is the same situation here. So now the heart has to push against a less open vascular system. So when heart has to push, it would keep becoming muscular and muscular by pushing, and it would keep becoming thick, and that is actually going to cause the heart to fail. So that is cardiovascular system. Hypertension would occur because the blood vessels are narrow. Hypertension would occur because they are atherosclerosed because of the glucose. Hypertension would occur because there is inflammation in the blood vessels everywhere. And then hypertension would occur because heart is trying to pump with force and it has become stronger. So that is cardiovascular system issue. So then if you continue to the autonomic nervous system, the nervous system that is controlling the heart, that is controlling the blood vessel lumens, that is controlling the GIT movements, that is controlling our micturition or urination or fecal excretions. Those nerves, when they would get damaged, And what is the damage? Number one, less blood supply to the nerve because of glycation, or because of the myelin sheath destruction because of osmotic pressure. Eventually, autonomic nervous system would stop functioning correctly. So a diabetic would start developing cardiac arrhythmias or rate changes, which their body would not even know that their heart has become fast. Why? Because when my heart becomes fast, and if I'm healthy, my heart and the sensors on the heart and around the heart and in the blood vessels would tell my brain that, hey, the heart rate is high. And brain would try to control it. But if the sensory systems are not working, nobody's going to tell the brain that the heart rate is high. Now heart is just going on by itself without much control. Similarly, when the damage would start occurring to the nervous system for the bladder or for the fecal, for the colon and anus, we'll start having other issues. Let's go down to kidney. Kidneys are, the poor things are very much affected by this. And now what is happening is, we know inside the kidney, so let's say this is a nephron, and this is the Bowman's capsule here. Then this is the proximal convoluted tubule. So these are parts of the system that makes urine. It's a tiny tube. So proximal convoluted tubule, then there is a loop of Henle. So descending limb of loop of Henle, hairpin turn, ascending limb of loop of Henle, then distal convoluted tubule. Then it would open up in the collecting duct, and then this would then bring urine out all the way to ureters, and then from there to bladder, from urethra and outside. This little tube, imagine the problem here. Number one, the blood arrives in this tube and gets filtered here. From that blood which is filtered here, or not exactly, blood cells do not go here. The filtrate does not have blood cells, but it has other things. Those things are then, we work on those to get those things back, what we need, and finally it becomes urine. But think about it. The problem is, number one, the blood vessel is non-enzymatically glycated. So the blood perfusion of the kidney is not correct. And kidney is, as you know from angiotensin system, which we've been talking about with COVID all the time nowadays, kidney is a very important helper for blood pressure control through angiotensin system. So if kidney itself doesn't know what is the blood pressure because the pipes to the kidney are clogged or narrowed, kidney would never know exactly what is going on. And if they are narrowed abnormally, kidney would always think that the pressure is low. And it would always try to make more and more angiotensin system to say, raise the blood pressure and increase the cardiovascular activity and increase the tone of the blood vessels or reduce the lumen. And kidney would abnormally create higher blood pressures. At the same time, kidney would start getting damaged because of low perfusion of the blood. Kidney is very sensitive for blood perfusion. Then it will not be able to make correct composition of the urine. Then there will be so much glucose that is going out in the urine that glucose would take water with it. That is osmotic pressure. That water, when it goes out with urine, with the glucose, the person would be urinating a lot. When they would urinate a lot, they would then drink a lot of water as well. So they are urinating, that is called polyuria, and they are drinking, that is called polydipsia. So now they have a problem. They're waking up at night and they're urinating, and then they're drinking water and they're urinating, and there is a problem going on there. Eventually what happens is, because of this glycation, because of low perfusion, the kidney just keeps getting damaged, and in 10, 15, 20 years, it fails under all of that mud that is collecting in it. So then if you go down, let's say to feet, diabetic feet, what happens there is, what is going on with the diabetic foot? So if you see here, let's say this is the foot. So let's say this is our foot. This is one of the most distant part of our body, just like our toes. And the first problem is that the blood vessels continue to become thinner and thinner as they divide and divide and go to the distant parts. So somebody who is diabetic, their blood vessels, everybody's blood vessels are already very thin when they go near the end of the body, that is feet and hand. You further narrow them by non-enzymatic glycation. And now we have another problem. There is less blood supply to the foot. When there is less blood supply to the foot, there are going to be injuries there because ischemia is occurring. On top of that, if there is injury and that causes infection, that infection is not going to heal correctly because one, there is less blood supply, and second, there is less immune system function there. Thirdly, the person would actually not know that I'm getting injured because the nerves that are going there, they have the myelin sheath of the nerves damaged. So the nerves are not really conducting correctly. They're not telling the brain correctly that there is an injury and we should feel pain. And then on top of this, the blood supply of the nerve itself is not very good because the diabetes has caused glycation of that as well. So that is what causes the diabetic foot, to the point that it could become that there is enough obstruction of the blood supply that gangrene comes in. Or when there is an infection that happens, that can result in gangrene because the whole system, blood supply system and protection system, is gone. So from head to toe, this is how diabetes causes its effects. And if you see, all of them are either non-enzymatic glycation or the osmotic pressure issues, or a combination of them. So let's stop this here. We'll continue to talk more. I think I did not even see what's going on the chat, but I hope everyone is okay and you're not too bored. So let's do this. I'm going to share the Zoom link and let's do some Zoom a little bit as well. So here is the Zoom link for today. So please like, subscribe, and share. And there are 3 links in the description. One is to buy me a coffee, another one is for the Patreon, and the third one is to support this work. So thank you very much. There is a link here. Odrasir says, Dr. Bean, watching your drawings has become oddly satisfying. Your lectures are sublime. Thank you very much. You're very welcome. Sepal Steve says, great discussion, doc. That's why diabetes is such a severe disease, as it affects multiple systems over time. Extremely bad process without a good cure. Yeah, so we'll talk about how to manage this. Christy says, that was excellent. Thank you. Awesome. Artie says, great class, doc. I will have to watch the video again. Got distracted for a bit and was lost when I returned. Can we call Dr. Fauci? Has been has been used here by a much better cool bean than Fauci. Okay, cool. So want to do some zooming as well? So I'm gonna hang up here. I hope that Aliji says, excellent, excellent, excellent. You're welcome. So once again, I'm going to just put the link out here. Please take this link. I would hang up here and I would start Zoom and we would then join there. Loretta says that I wish I could join the Zoom. I already have a Zoom commitment from USA every Friday night. No worries. We will miss you, but we would talk to you later. Susan says, love tonight's lecture. Thank you very much. Cool. Let's do Zoom. Lenny says, great explanation. I talk with clients about glucose handling all the time as a clinician nutritionist. Really great picks and easy understanding. Thank you. You're very welcome. All right. So see you soon.